In number 6 here, we have this matrix, and do you see that it is regular? Because even to the first power, all the entries are non-zero, so it's regular, and regular matrices reach a steady state. And that's what we want to do here, is we want to try to find the steady state vector for this matrix. So let's start here by letting x, so we will let x equal the steady state. Now it's a 2 by 2, so we'll have an x and a y for each state. And then what we're going to do is try to solve this matrix equation. Tx equals x. And what that means is that when we apply the transition matrix to our steady state vector, we get the steady state vector right back. So let's write this out. Now we're going to get, by going across the rows, we'll get 0.2, 0.3, 0.8, 0.7 times the steady state, which is xy, and we will get xy back. Let's multiply. Now we know to multiply, we go across and down, right? First and first plus second and second. So let's do that. So we are going to get 0.2x plus 0.3y, and then, right, second row, first column, first and first, second and second, over and down. So this is going to give us 0.8x plus 0.7y, and that's equal to this matrix, xy. And now we know that two matrices are equal if they're equal component-wise. So this component must be equal to that component. This component must be equal to that component. So let's set those equal. I'll do it up here at the top here. We're going to get 0.2x plus 0.3y. That's equal to x. And then 0.8x plus 0.7y. That's equal to y. And now we've got a system to solve. Now, when we solve our systems, we want all the variables on one side and the constants on the other. So right now we've got x's on both sides, y on both sides. So let's subtract x, then we'll subtract y. So when we subtract x, we're going to get 0.2x minus 1x, right? That's a 1 there. So what we're looking at here is, 0.2 minus 1, which is negative 0.8. So our new equation is going to be negative 0.8x plus 0.3y. That's equal to 0 now, right? Because we subtracted that x out. And in the second equation, we're going to subtract this y, so we're going to get 0.7y minus 1y. What we're looking at here is 0.7 minus 1, which gives us negative 0.3. So our second equation is going to be 0.8x minus 0.3y equals 0. And we notice that this second equation is just negative 1 times the first equation. These two equations are equivalent. So we don't really have two independent equations. What we're going to get here is no unique solution. So what we're going to do is eliminate one of these equations and find an independent equation. Now, here's what we know. We know back here, in our vector back here, we know that x plus y has to equal 1, so we're going to write that. So we know now that x plus y equals 1. So we could solve this system here. We could go with negative 0.8x plus 0.3y equals 0. And we could even keep this other equation if we wanted. Won't do any harm. Negative 0.3x equals 0. And the new one, x plus y equals 1. Or if you wanted to, you can eliminate one of these equations. So what we could do if we wanted, we could eliminate, say, this equation here. We could just cross that one out, and we could go with this system here, negative 0.8x plus 0.3y equals 0, and then x plus y equals not 0, that's a 1. We could go with that system. Now we're going to do it on our calculator, so it doesn't really matter which system we use, the 3 equations or the 2 equations. I think by paper and on the board we've done this one over here. So what would happen if we did this? Let's put this into matrix A on our calculator. So matrix A is going to look like this. We're going to put in negative 0.8, 0.3, 0, 0.8, negative 0.3, and 0, then 1, 1, 1. And what we're going to do is we're going to RREF this matrix, negative 0.8, 0.3, and 0, 0.8, negative 0.3, 0, and 1, 1, 1. Now when I do that, I'm getting this. I'll just go down the columns. I'm getting 1, 0, 0, 0, 1, 0, and then I'm going to round off here, 0.27, 0.72. Actually, if I round this off, this comes out to 0.73, so let's go with that. And then I'm getting a 0 here. So what this means, right, this is our x column, our y column. So we're getting here that 1x, no y, so x is 0.27, and y is 0.73. And then we get this row of zeros because it has to do with maybe these two equations being identical. So we're going to conclude now that x is equal to 0.27, y is equal to 0.73, and so our steady state, what was that? So our steady state is this. X equals 0.27, 0.73, and it means that 27% of the time will be in this state and 73% of the time will be in this state after we go long enough. So in the long term, here's our vector.